Okay, 8:18. So let's get started. First of all, I know I'm only you answers and homework gradings for first 5 homeworks, just because of the fact that the first couple of weeks is always hectic. I'm trying to get at least three, hopefully by the end of the week, to get three homeworks graded and get back to you by the end of the week. If not, hopefully by mid of next week. Other than that, if you have questions, send me an email. Recently, I'm a little bit busy, but I'll try to respond. And another thing is, remember that every Wednesday, every it should be every uh, two Wednesdays, every the other Wednesdays, meaning that we have a session this week, and then next Wednesday at 8 p.m. I will be hosting office hours. So it's alternate. If we have a session this week, we don't have a office hour. If we don't have a session this week, then we would have a Wednesday 8 p.m. Office hours. So in case you have any questions, you can go there, dial in, and ask me questions there too. So let's continue with the contents of week 5. Week 5, you already actually finished the homework for last week, but we can continue and try to go over some of this. Okay, for week 5, the basic idea here is the chapter 6 of the book is discrete probabilistic modeling. I'll start with an introduction and discuss a little bit of the probabilistic modeling with discrete systems, and also study the modeling component and system reliability, followed by the discussion of linear regression and homework. So we have been developing models using proportionality and determining the constants of the proportionality, which was covered by the first 2 chapters. In this chapter, we will allow the constants of the proportionality to vary in a random fashion rather than to be fixed. So last time we briefly explained Markov chain. So if you look at this particular transition probability type of problem from state to state, from state 1 to state 2 have a certain probability with 1 minus p, and then the probability of staying at itself is a probability of p, and then probability of staying at state 2 to itself is q. And on the other end, the probability of transferring from state 2 to state 1 is 1 minus q. So if you know that this actually is the same as a matrix, right? If you write it as so let me didn't realize we have this fancy thing. Oh, this is nice. I didn't even know. Okay. Um, Okay, actually, I want to write something, but in general, say let's get some paint. Um, so you can see the screen, right? Yes. Okay. So so essentially, what I'm saying is that transition state diagram is no difference between this particular probability. 1 to 1 is p, 1 to 2 is 1 minus p, and 2 to 2 is q, and 2 to 1 is minus q, 1 minus q. realize that, pay attention that 1 to the whole row should add up to 1. Just simply because that it will transfer somewhere else or stay at its current location. So that's why this add up to 1 for any of the transition matrix problem. So in this particular case, if we continue, if we look at this, yes, we're still on, yes, 6, okay. Not supposed to be week 5. Okay, my bad. Okay, continue. Yeah, it's right here. So as we just discussed, it's a transition probability problem. And then the model interpretation is if the 2 branches begin the year with a total of n cars. This is a modeling problem between 2 branches of the rental cars, I believe, right? So in the first branch, because some people would take the car from branch 1 and then drop it off at branch 2, and then historically we should be able to model this empirical probability of this P and Q and 1 minus P and 1 minus Q. We can get that probability there. Then in the long run, we want to figure out, in the long run, approximately what percentage of the cars will be in Tampa and what percentage of the cars will be in Orlando. So assume that this is a rather simple problem, only have 2 states. Suppose that we have a system of locations. And then essentially this type of approach can help us to make a decision on, okay, since I know 57 of the cars will be in Tampa at the end of the year approximately, so we want to study what percentage, how could we maybe move some of the cars by the company to move the cars on purposely from Tampa to Orlando if it turns out to be we have a lot of demand in Orlando in that case. So that's something that the company can make a decision on. That's why this type of approach can help the company to make some decision like what I just discussed there, and then help them to use mathematical models to make a rather sound decision. Even though we can argue that sometimes it may be difficult to estimate the empirical probability of P and Q. It really depends how well the data collection process is. Okay, so based on that, so essentially we're saying that this, at the next step, Qn plus 1 is 0.4 P plus 0.7 Qn, and then Pn plus 1 is 0.6 Pn plus 0.3 Qn. That's a lower curve. And then on longer term, 57 will be in Tampa and 43 will be Orlando. This is a problem. I mean, this is a case study from the textbook. So, and then let's try to model another problem, voting tendencies. And then for different Republican, Democrat, and Independent, they have certain probability to vote some other parties members. It could have that. And then we have those 3 representation of those 3 curves, and then we want to try to find out the long-term probability that which one have a higher chance to win. So essentially, it also helps us. You can also consider that as some sort of equilibrium in the system. Okay. And then the book actually continued with some modeling component and system reliability. And the reliability of a component or system is the probability that it will not fail over a specific time period. Okay, hold on. Someone has a question? No? Okay. Okay, so essentially that we're saying that let ft be the failure rate of an item or component or system over time t. So small ft is a probability function, and then we can use rt is 1 minus ft. Big ft is the cumulative function of the Philip function. So rt is the reliability of the system, meaning that if it's the probability that is not failing for the system. So for a series system, it's very much like what we studied in high school for the electricity currents, right? The series system, the reliability is uh, the reliability of each individual multiplication of each individual component. So RST, the system reliability equals to R1T times R2T times R3T. And then for a parallel system, it's the probability of individual component being reliable minus the probability of the reliability of the individual component that their individual reliability. And then series and parallel system would be a combination of both of those two depending on how it's set up of the system. Continue with this discussion, we want to actually give you a little bit more mathematical perspective of linear regression. You probably have an idea on what is linear regression. Essentially, we're trying to have some discrete points, and then we're trying to fit the line. Hold on, let me get my pen. So for for linear regression, the whole idea is we have certain points, essentially meaning certain observations of the independent variable. Suppose that we have a x and then we have a y, and then we want to fit. This is our observation here, black dots. And then what we really want to do is we want to try to fit a line, even though this line is not straight. You know the idea. We're trying to fit this line to see that it can minimize some sort of model error. And then previously in chapter 3 or 4, I think we discussed that we want to have some sort of metrics to explain how well our model is. And then we can fit the line like that. We could also fit the line maybe something like this, even though this looks like a little bit off, things like that. So there are multiple possibilities that we can fit the line. And then which one actually is the best in terms of which metrics. That's the whole idea of linear regression. And then the whole idea of least square linear regression. Let's say how the least square itself is defined. So essentially here it's only one variable x, and then one independent variable which is x, and then with one dependent variable which is y. Remember that in the regression framework we always discuss independent variable and dependent variable. And then independent variable is usually x1, x2, x3, etc., etc., and then independent variable majority of the time will be y. So in this case, we have yi equal to axi plus p. As you can see there, it is linear regression only because the relationship between y and x is linear. It has a constant of a and an intercept of b. And then we have 1 to m data points. We have m observations there. And then in order to solve this problem, what we can do is we try to we have a normal equation which is actually defined this way, even though the whole idea is that we try to minimize the error, predicted error. So maybe it's worthwhile to bring up here. So the whole idea we're trying to do is y predicted value minus yi, which is the observation, squared, sum. Sum of this squared, how to sum? I equal to 1 until all the way to m in this case. That would be our squared error, sum of squared error. And then what the whole purpose of linear regression is trying to find a y-predict so that we can minimize this probability, minimize this matrix. And then as we started earlier, we said this has to be certain constraint, right? The constraint would be this ST is subject to 2, which is also the constraint. You would see that actually in this week's lecture, chapter 7. I hope you already read some of those, and then you know what I'm talking about. So ST is subject to, and then in this case, we're saying that subject to y itself is predicted by ax plus b. And then x is, we can say that a is a constant, b is a constant. That's all. That's the problem we're trying to solve. And then suppose that we can use some sort of normalization that the essentially this in order to solve get a minimal of this, what we can do is we can take the second order derivative and then try to solve a and b. So essentially ax plus b. So this problem can be represented as ax plus b, that's our y hat minus yi squared. That's my objective function, right? If I consider this as z, if I take the partial first order derivative of z in terms of x, I can get a function, and then take the second order derivative of x, z in terms of x, I can set them both of them equal to 0. Two unknowns and two equations, we can find a and b. That's one way to solve this minimization problem. And then, as you can see here, even though we call it linear regression, we translate the linear regression itself to a quadratic programming problem. Quadratic programming problem, what it is, the objective function is a quadratic, and then there are some certain constraints. And then in chapter 7, we are going to discuss linear programming, which is a fundamental form of the optimization, even though this quadratic programming is a little bit more advanced compared to linear programming. But linear regression is translated to a quadratic programming problem. Okay. Hope you have already read the book for chapter 6, and then you would know that best fitting line would be defined as, after solving those two system equations, we can solve a and b as being this certain form. And then we would know that the error sum of squares is minimized in this case. So it's called sum of squares of error, SSE, is yi minus this. Essentially, this is our objective function that we just discussed. And then there's some other definition of SST and SSR. And SST is the total corrected sum of squares. That is each individual observation minus the mean of all the observations sum square. That's SST. And then regression sum of squares is defined as SST minus SSE. And then we can define R squared being 1 minus SSE divided by SST. Remember that R squared itself is a strong indicator of how well your fit is. And also try to remember that this R squared is only defined by linear regression. Even though in many of the nonlinear regression and some other advanced general linear models, we can generate R squared, but it doesn't mean the higher R squared, the better fit. It is only applicable to linear regression. If R squared is higher, the better fit for linear regression. We cannot always use R squared to judge how well the model itself is. Okay, so the book actually also discussed the residual plot. It's very important to look at the residuals to understand how well the fit is. I'm sure that actually I assigned a homework on this on the residual plots, even though I didn't get a chance to read your homework yet. Hopefully, your submission yet. Hopefully, you guys got a better understanding of this. But in general, what we are looking is whether the residual itself is random. If it's not random, it has certain shape. For example, this one essentially saying that as x being larger and larger, the error is being bigger and bigger, right? So that's essentially meaning there's some sort of bias in your model. So you have to try to address those. It could be the model is misspecified. It could be the data is has some outliers. So if the model is misspecified, you can always try to correct with a different model. And then if the model has the data itself has outliers, before you start looking, you should do some sort of data study to understand the data, and then drop those outliers. So let's say what is the outlier? So for x and y again, so if we see some data points just like this, we know, wow, this is if we want to fit a straight line, looks nice. If we actually saw some point here, we pretty much know these are outliers. We have to remove those points. That's a nice smiling face. Okay, we have to remove those points before you actually start the linear regression fitting. Because if you remove them, you would fit this. If you don't remove them, you probably have a really difficult time to find the fitting line. The fitting line could look like that, right? And then it will not be a good fit. We know it will not be a good fit. The error of the prediction, this is the predicted value, this is the actual value for this particular x. You see how much difference it is, right? It would be a lot of error there. But if we remove those outliers as I could use different color for the outliers. And then if we remove those outliers, then we would see that the error itself would be muted, and then the model could do a very good job in terms of the prediction, in terms of fitting the model, in terms of fitting the data, in terms of the prediction as well. Okay. And then another type of shape that we would pay attention to would be, like I said, for the first time is a fanning shape, and then it says the higher the value, the higher the error, even it's on a different direction. One is positive, the other one is negative. And then it could be linear. The higher the error, the higher the x value, the higher of the residuals. The residue and the error, essentially. And then this curve linear, meaning that somewhere in here it's not doing really a good job. What we're really looking for is a type of randomness of the residue. And then that randomness should show something like this, meaning it's relatively speaking, it's on x-axis, on y-axis. In general, we don't see this apparent difference between. We don't see these apparent shifts in the residual plots. Okay, that's pretty much very much a snapshot of what is linear regression. I definitely assume that you should have read the book. You should understand much deeper than what I'm covering here. What I'm really trying to do is trying to cover the gist of the methodology itself. And then this is a homework. I'm sure you have already done that. So let's continue. This is a week 6 material, even though we're covering chapter 7 of the book. Okay. Which I don't know which screen you guys are viewing. Is that this one or chapter 7? Which one you guys see?
It's the one that has your PowerPoint presentation on it.
Is chapter 7 or chapter week 6?
It says ISDA 609
Oh,
mathematical
okay, okay.
modeling.
It's a different window somehow. Maybe let me see if I can show you the second. Okay, it looks like we can. Okay, so continue with this. For chapter 7, we really just started think about optimization problems. And then we go through optimization of discrete models and start with the introduction and there's an overview of optimization modeling. And section 7.2 has linear programming 1 geometric solutions and followed by 2 algebraic solutions, and number 3 the simplex method, number 4 is sensitivity analysis. And section 6 has a little bit of numerical search methods followed by homework, but what our focus will be really on sections point 2, 3, 4, and 5. And then the meat of this chapter is really section 7.4. Okay. So in chapter 3, we discussed that 3 criteria for fitting a selected model to collection of data. It's minimize the sum of the absolute deviation, minimize the largest of absolute deviations, and also minimize the sum of squared deviation. Least squares criteria. Essentially, the number 3 is the least square method that we discussed for linear regression just now. And then for chapter 7, let's look at what is a linear program. Linear program is, we discussed this in our first introduction section, but we can continue with this, try to have more detail on what it is. So what we're trying to do is trying to minimize R, which is a linear combination of independent variables, some sort of linear function, and then subject to a certain constraints, which is r minus ii larger than or equal to 0, or r plus ri larger than or equal to 0 for I equal to 1 to m. This is a function is trying to find some sort of point on a line or something. I couldn't remember the exact analogy here, but I'm sure it's there, right? So you understand that part. So, and then remember it's just a linear regression, a linear program. It's a linear programming problem. And then consider with this, the basic model is trying to optimize certain function and then subject to a linear constraint. And the constraint itself could be larger than equal to, and then could be equal to, could be less than equal to. And then that subject to usually can be in shorthand as S dot T dot, which is the subject to, which are the constraints. And so that in this case, we call those x's being the decision variable, and then we call this function optimize fx. Okay, we're calling that this is the objective function, and this part is the we call this part of the objective function, and all the x's being the decision variable, and this part being the constraints. And then very interestingly, one more thing that you have to remember, that the right-hand side, which is all the right-hand side of b's, which is bi. In this case, I I is part of a subset, part of a superset of all I, capitalized I, and J is a subset of uh, the superset of the J, capitalized J. And then these are some ways to classify some optimization problems. It could be unconstrained, could be constrained, and then it could be a linear program. And then let's say what is a linear program. There is a unique objective function. Decision variables have power of 1, and then no product of decision variables in the objective or the constraints. Otherwise, if we have xi times xj being the in the objective function or in the constraint, then it's no longer a linear program, becomes quadratic program, right? And then the coefficient of the decision variable in the and then the coefficient of the decision variable in the objective function and each constraint are constant. All the a's or b's are the constraint. And then on the right hand side, usually we actually use b's. And in the decision, I mean the constant will be a, c, pm, any of the constants that we can use. And then the decision variable are permitted to assume fractional as well as integer values. This is a key difference between a linear program and an integer program. And then the integer program will not be permitted, for the decision variables, not be permitted to assume fractional as a value. If, for example, if we want to decide on how many chairs or how many tables that we can produce to maximize the profit of a specific firm, then we cannot take fractions for those decision variables. That's the key difference between a linear program and linear program and integer program. There are other types of programs, including multi-objective or goal programs, nonlinear program, dynamic program, stochastic program, and integer program. Okay, so you just asked. Pasha asked what is decision variable has a power 1 means. So essentially that is this decision variable xi is powered by 1. So essentially it's just xi. It is not xi squared or xi times xj. That essentially would be no longer be powered by 1. No cross product. That's the whole point of linear program. For example, we see that we want to as the example that I just mentioned, if we want to make a decision on how many chairs and how many tables that we can make, then we can maximize. Suppose that each chair xi can give a certain revenue, R1. This is something that we know because we know how much share each share can sell. R1 plus X1 is the chair revenue, and R2 plus X2 is the revenue from all the tables. And then we can say that we can use a cost function, say that C1 minus the X1 minus C2 X2. That would be my objective function. It's simple example that I'm thinking of, right? We have two types of products that we can generate. One is x1, the other one is x2. We use amount of x an amount of type 1 product that we can produce as the decision variable, which is x1. And then we can say that the number of tables that we can produce as a second decision variable, which is x2. And then correspondingly, we can get the maximized revenue minus cost, get the maximized profit, but subject to maybe certain budget constraint, right? maybe x1 can and maybe x1 plus x2 cannot be larger than equal less than equal cannot be larger than equal to 20. So we don't really want to produce more than 20 units, something like that, right? Oh, I don't want to produce more than 5 units of x1, etc. And then we can say in this case we can say x1 is integer, x2 is integer. That's all constraints. And then x would be decision variable, x2 would be decision variable 2, and then this is powered by 1. That's the idea of powered by 1. It's not x1 squared. Otherwise, this becomes a quadratic program. It's no longer a linear program. And then, as you can imagine, you can use log x in the objective function. You could use exponential x in your objective function, even in the constraints. And then all of those will become nonlinear programming problem. Okay. And then actually, let's go back there. It also says that no product of decision variables in the objective show constraints. No x1 times x2. It becomes nonlinear as well, or quadratic, right? Okay, continue. As we continue with the discussion, there will be problems of nonlinear program, dynamic program, and also stochastic program, including stochastic linear program and stochastic nonlinear program, etc. And integer program. And then in this particular course, we're actually mainly covering linear program, integer program, and a little bit of nonlinear program, so that you can get a sense on what it is, and then you can understand what is the optimization. Not necessarily you need to know how the function itself, how the optimum solution can be derived mathematically or numerically, but at least you should understand what's the function form. And then that way, when you start reading some of the literature on some other machine learning and data mining methodologies, you would realize it's all well connected to the math programming problem. Okay, continue. Yeah, the example on the book has a space shuttle cargo problem, and then we say that if item j is taken by y, then yj is 1. Otherwise, if it's not taken, then yj is 0. It's actually a classic example. We call it knapsack problem, which is, let me write it here. I didn't realize we can use it here previously. Maybe this is something new for knapsack problem. Suppose that you have a knapsack, a box that you want to carry with you for camp, and then you say, okay, I can only bring maybe 2 bottles of uh, 2 pieces of cookie and 3 pieces of some 3 bottles of water, etc. But I want to maximize my profit coming from this knapsack, because as I mentioned earlier, I don't really know. I should know that what's my objective function look like. Maybe uh, a bottle of water in a camp helps me happier or make my life easier, and I can sustain less food, but I cannot sustain with less water or some other problem. But that's a knapsack problem, trying to maximum some type of objective function, and then subject to the limited space that you have in the knapsack. So this is very much similar to what we have for the uh, for the um, for the um, for the knapsack problem. So what I'm saying is this problem is very similar to this. Okay. And then there's some other things for nonlinear programming. nonlinear problem, we see that we approximate by a piecewise linear function. Piecewise linear is defined as piecewise, meaning it has multiple pieces. So if we can actually fit the function like what we saw on the right hand side, and then it's really a linear function by pieces, meaning that from 0 to a1, it is a linear part, and a1 to a2 is a linear part, and then a2 to a3 has another linear part, even though the slope of all those three pieces are different. They are all approximation of the original problem. And then essentially you can see that instead of nonlinear optimization program, it's actually was translated to a linear problem, and then with certain constraints that was defined there. And then if another thing that we can think about here, it would be we could use how to use this piece linear function to approximate the uh, nonlinear part. We can say that each single piece is a separated problem. We could use regression to solve that linear function, and then use that linear function as a proxy to solve the overall problem, right? So essentially, what I'm trying to say here, this piece is a linear regression, this piece is a linear regression, this piece is another linear regression. We use three pieces of the linear regression results as an input of this optimization problem to solve the slope in this case. To solve, no, to solve the x1, x2, x3, and y1, y2, and y3 in this particular case. And then continue with the discussion of linear programming. Let's look at geometric solutions. And this is our carpenter's problem. We're trying to maximize the profit that we can generate by x1 and x2, and then subject to lumber and labor constraints, and also the non-negativity constraints. And then what is the objective function? If you remember that a z function equal to, let's say, y function that's equal to 25x1 plus 30x2 is really a set of lines that's parallel to this particular line. When x1 is 0, y is 30. And then when x2 is 0, y is 25. So apparently this, oh, my bad. This is the first constraint. This is the first constraint. That's saying that when let's look at this actually. This is a first constraint. When x1 is 0, x2 at maximum can only be, x2 will be 24. Should be 23. Yeah, here, right. When x1 is 0, y should be 23, right? So that's this point. And then when x2 is 0, x1 should be 34.5. That's why this is the first line, first constraints. And then we said that all the x and x1 and x2 cannot exceed 690. This is a line. So anything below here would be the region that's feasible for the first constraint, right? For the second constraint, when x1 is 0, x2 is 30. It's right here. And then when x2 is 0, x1 is 24. It's right here. So this is the line for the second constraint. And then we have to satisfy this relationship that x1, certain x1 plus 4x2 less than or equal to 120. So it's also on this side. The intersection of those two constraints would be on here, or going down here, even here, right? But we said that we cannot have negative number and negative number of units of labor, so that we have to say x1 is larger than equal to 0. That's on this side. That's essentially another constraint, and then it's on this side. And then the fourth constraint would be x2 is larger than or equal to 0. It should be on that side. Everything on that side. And then we take the union of all those four pieces. We formed the feasible region. This piece, this region is defined as the feasible region for this particular problem. And actually, before we move on, I should mention that the objective function is 25x1 plus 30x2 is this. So it's a moving piece, keep going anywhere, and then it can happen here, can happen anywhere here, but it's parallel lines to this dotted line in this graph. That's the objective function. And then the problem is, how can we solve it, right? So suppose that this is the feasible region, and then this is our objective function. So objective function decreasing going there, objective function increasing going that direction, and then in order to minimize our objective function, that's our solution. What is the solution? Solution is a decision of x1 and x2. That's the problem that we are trying to solve. That's our decision variable, right? And then where the value is maximized, it is here in this particular case. Objective function a1 plus bx2 is maximized at this point. And then you might have started wondering already, would linear program always have the best solution at all the extreme points? The reality is, it happens that actually can be proved that it always happens at the extreme points. And one of the major characteristics that this being holding true is that the feasible region itself is convex. And then what is convex? What's the definition of convex in mathematics? I'm not sure if you still remember, but actually I want to give you a little bit idea here. If we see that the function is convex, we're essentially saying that any of the points inside the function, suppose I call it, if we say that the shape is convex, any of the points inside this shape can be a linear combination of any other 2 points. That's the definition of the convex. And then why this is not convex? This would be a concave function because some of the point, any of the point we are saying that should be able to be defined as a linear combination of those two of the points. But in this shape, let me think. Yeah, the idea is essentially is, for example, this is a vector and then this is another vector. We should be able to find, using linear combination, to find this vector. And then in here, we wouldn't be able to do that, even though I have a difficult time to explain that at this point. But that's a whole, that's a general gist of the idea. I can do a little bit review after this session to give a better explanation on the concave function. Uh, but here, but here the idea is because the feasible region is always convex, and because of the major reason, the objective function attain both a maximum and minimum value occurring at extreme point of the region. This is the theorem one of this part, so you should review that why it's happening there. And then how can we algebraically find the solutions, right? That's one way. Section 7.2 that we just discussed, we can look at using graphically to figure out the solution. And the 7.3, we're saying that we algebraically we can solve it. What we will do is find all the intersection points of the constraints, determine which intersection points, if any, are feasible to obtain the extreme points. Find the and then evaluate the objective function at each extreme point. Choose the extreme points with the largest or smallest value of the objective function. So essentially saying that it's more like an exhaustive search method. You have to list all the extreme points and use the extreme point values to evaluate your objective function and then pick the best. What is the best? Is it the maximum or the minimum? If it's the maximum of the maximum problem, then the maximum itself is the best. And then if the minimum problem and then the minimum of all the set is um, it's minimum. So you are So Torsey was asking, that doesn't it always happen as a vertex? Yes, it always happens as a vertex, and then that's why I'm explaining the convex idea. But if it's concave, it's not. It happens that for all the linear program, the feasible region is convex. And then that's why actually linear program and integer program also have this name called convex programming. Okay. And then in terms of the in terms of computational complexity, we have to enumerate all the intersection points, right? So that's why it comes to our next methodology, which is called simplex method. We get smarter about which extreme point we should evaluate for the next step. So the step of the simplex method is called, first of all, you need to set up the tabular format. Place a linear program in a tabular format that will be explained a little bit later in the textbook. Okay, and then you find the initial extreme point. The simplex method always begin with a known extreme point, usually the origin 0, 0. And then you try to do two things. One is the optimality test, and second is the feasibility test. For the optimality test, you determine whether adjacent intersection point improves the value of the objective function. If it's not, the current extreme point is optimal. If improved is possible, the optimality test determines which variable currently in the independent variable set having value 0 should enter the dependent variable set and become non-zero. And then second test is a feasibility test. To find a new intersection point, one of the variables in the dependent set must exit to allow the entering variable from step 3 to become dependent. The feasibility test determines whether current dependent variable to choose for exiting ensuring feasibility. And then after 3 and 4 is done, you try to pivot the tableau and then from a new equivalent system of equations by eliminating the new dependent variable from the equation do not contain the variable that exited in step 4. then sets a new independent variable to 0 in the new system to find the value of the new dependent variable. So this whole process, 3, 4, 5, is something not not new to you. It should be something, if you look at the text, you would realize it is the some approach that we studied in high school is called elimination method. So trying to eliminate certain variables and try to bring in some other variables into the equation. That's the gist of the problem and the gist of the methodology. And then you repeat step 3 to 5 until optimal extreme point is found. And then in the textbook, just go through the example from page 273 to 278, and then it's very go through this example very carefully to on how to solve linear program using simplex method. And then in the homework I have asked you to try simplex method. You probably would wonder, can I use R to solve this problem? Not yet. Even though later on when you started using it, you probably would be solving it using some sort of optimization solver to solve your problem. But at this stage, you're still trying to learn how the simplex method works. As a homework, you should be able to solve at least one of the questions by hand using simplex method. And then you could write it on a paper and take a picture, put all together as a PDF, send to me. I don't mind. Or you could write in nice format in the Word format, etc., to solve each tableau one step by step. That doesn't matter. But please do not use R to solve the problem. Okay, and then continue with this, the sensitivity analysis. Sensitivity analysis is trying to do is the sensitivity of the optimal solution to changes in the coefficient of the objective function. So the idea is, what is the effect of changing the value of the profit for each table, one of the decision variables? So if how much change that would be. So essentially, that gives some sort of what if analysis potential for the problem itself, because that will be defined as from a business perspective. If you have a solution for these what if scenarios, you would be able to be better informed in terms of what type of business decision that you need to make. Because anything that we're going to study mathematically could be very beautiful, but in reality, we should have some reality check to understand the sensitivity of the problem itself, right? And then there's another type of sensitivity, changes in terms of the amount of resource available, the right-hand side. If the right-hand side changes, what's the effect of the change of the objective function if one extra resource is available? And then in terms of economic interpretation, it's a marginal value that the extra unit of lumber or extra unit of labor can bring to the objective function. So that's two types of sensitivity analysis, and the textbook has a very nice detailed discussion there too. So that's pretty much that what we are going to cover, even though the last section of the textbook mentioned a little bit about numeric search method, which is more relevant to the nonlinear programming problems that we will cover later on. But let's quickly look at this, some sort of unimodule function on the interval a and b, and then we know there's a global maximum idea here. Global meaning you would always be able to find that maximum, and then a function could be not unimodule, meaning it have a maximum, it also have a minimum in a certain range between A and B. And then we can, I hope that you have studied some of this approach already previously in some of the computer algorithms. We could use dichotomous search algorithm to find the maximum value, meaning you always evaluate the midpoint and then If the midpoint is bigger than one of them, you just pick a new midpoint. Just keep going, and then eventually you will be able to find the maximum solution in this particular example. Okay, continue with that. We can also, instead of using mid point, we could use golden section search method, meaning are the first piece and second piece um, have a certain ratio that helps, which is called golden section ratio, golden section search method. These are the homeworks for this particular chapter, and then as always, you can pick 3 of them and finish them. And then let's see, some people probably have some questions that I ignored earlier. Oh, okay, this is a very good question. So Classy was asking, in the example we saw, the right-hand side was less than equal to. What is the best way to deal with larger than equal to? So if we say that x1 plus x2 larger than equal to 3 as a constraint, it's actually straightforward for you to, what you can do is you can change this to negative x1 minus x2 less equal to negative 3, right? You just times the negative 1 on both sides, and then it becomes a less than equal to form. And then if you pay attention to the textbook, that it's always called, you put the tableau as a standard form. Standard form is always having less than equal to in the constraint. So meaning that any of the larger than equal to can be translated to less than equal to. And then of course standard form is beyond just translate to less than equal to. It also includes some sort of, we call it slack. We can introduce a new variable which is called y1, and then add that y1 to it, it becomes equal sign. And then this y1 is called a slack variable. That's very useful when you solve the problem using a simplex method. Let's say, okay, in here I didn't mention, the methodology didn't mention, but it's really tabular format. Place linear program in tabular format. The tabular format actually already explained it should be in the, it's called standardized form. Standardized form should be equality instead of inequality. If it's a larger than equal to, you can always translate it to a less than equal to. Meanwhile, you can add a slack variable, and so that you can translate to a equality constraint. That's a good question there. And then let me see if I missed some other questions. Okay. Brett had an earlier question there. Explain the emphasis of having b equal to 0. Or in an early chapter of the book. So essentially, okay, Brett was asking the emphasis of having b equal to 0 in a function of y equal to axb plus ax plus b function in the early chapters of book. I think it's really nothing. It's just that it's always depend on the problem itself, meaning that we specifically said that x and y have a linear relationship with no intercept. So I think it's more from some of the specific business situation or the specific scenario that they were trying to cover. So it's not necessarily, it's actually in terms of the usage, it's probably less prevalent for a case that b is 0. If b is not 0, it's probably more prevalent. Okay, looks like that's all. That's all the questions that I missed. Do you have any questions so far for me for today? No? Okay. If you don't have any other questions, please finish homework 7. Homework 6 actually, right? Chapter 7 homework, but it's really homework 6. Finish homework 6, and I'm trying, as I said earlier, I'm trying to get back to you on the solutions and the graded homework for first 3. Thank you, and have a good night.